Hello everyone, I am Dr. Alok Agrawal and I will be discussing today on course code ME 404 Fluid Mechanics, and the topic of discussion is compressible flow. Okay, this is the topic of Unit 5 Part 2. Let us start with this. So what is compressible flow? First we will see the introduction part of it. So compressible flow is defined as that flow in which density of the fluid will not remain constant actually during the flow. So till now what we have studied incompressible flow, and in that we have considered that while fluid is flowing, the density of the fluid remains constant. But here we will see that what will happen when the fluid density vary when it flows. Okay, so here the density of the fluid will not remain constant, and that type of flow is called compressible flow. Means point to point, when the fluid is flowing, at each and every point there are possibilities that density of the fluid may change. Okay, so compressible flow study is necessary in various situations, and some of the examples are while the flow is taking place in orifice and nozzles, actually when the gas flow to take place, because any gases is a compressible fluid. Okay, now flow of gases in machines such as compressors is also an example where the fluid flow in fluid flow density changes point to point because cross section area is changing in compressor, and because of change in cross section area density varies. Again, projectile and aeroplane flying at high velocity at high altitude, there also the fluid passing the jet or aeroplane or projectile have undergone with change in density, and they are compressible fluid. In all the cases, density of fluid changes during the flow, and this change of density of fluid is because of change in pressure or because of change in temperature or because of both. Okay, and hence pressure and temperature play important role in the change in density of fluid. Thermodynamic study of those fluid is very much necessary. Okay, some basic equations of compressible flow that we have already seen for incompressible flow, now we have to modify those equations for compressible flow, and those important equations are continuity equation that we have seen for incompressible flow. Again, Bernoulli's equation, or otherwise called as energy equation, also we have seen it for incompressible flow. Now we have to modify it for compressible flow, and the other equation is momentum equation. There is one more equation, that is equation of state, that is PV is equal to MRT, that we have seen in incompressible flow. So for converting that in compressible flow, what we have to do? We have to take M by V. PV is equal to MRT. So from left hand side, we have to move that V to the denominator of M, and we can replace P is equal to rho RT. That is the thing we have to do for equation of state. Now this three equation is very important. So we will start with continuity equation. In incompressible flow, we have seen that continuity equation is A1 V1 is equal to A2 V2. Now for compressible flow, we have to incorporate density term also there. So this based on law of conservation of mass, that is based on law of conservation of flow rate. Now it is based on law of conservation of mass, which states that matter cannot be created nor be destroyed, but it will remain constant. What does it mean? It means that mass flow rate will remain constant, because if there is a flow in pipe, if no mass is added in the pipe and no mass is getting out from the pipe, then the mass flow rate in the pipe will remain constant. So for one dimensional, mass flow rate per second can be written as rho into A into V, density into area into velocity. In case of incompressible flow, this density term was not there because in both the side density will remain same. So rho 1 A1 V1 is equal to rho 2 A2 V2. So rho and rho will cancel out, but here it is not the case. So as per law of conservation of energy, this rho into A into V will remain constant, and we know that differentiating any constant will give you a 0. So when we differentiate this, rho into A into V will get 0. Now as per product rule of differentiation, we have considered A, V as one function and rho is another function. So first function into differentiation of second function plus second function into differentiation of first function. Again we have to differentiate this A into V by the same formula, and what we will get? We will get this rho A dV plus rho V dA plus AV d rho. Now dividing throughout by rho into A into V, we will get dV by V plus dA by A plus d rho by rho equal to 0. And this is our continuity equation in differential for compressible flow. So this is very important. Next one is Bernoulli's theorem. See, from Euler's equation in unit 3, we have derived from Euler's equation this formula. And after this, we deduces that equation to Bernoulli's theorem by taking this 1 by rho as a constant outside the integration sign. But here, for compressible flow, this 1 by rho is not a constant quantity. So we have to keep this inside the integration only, and we have to differentiate it with this. So after differentiating, we will get Bernoulli's theorem for compressible flow. So here we have to consider two cases, okay? Because compressible flow is there, so we have to involve thermodynamics here. So there can be a two process. That first one is isothermal process, and second one is adiabatic process. So for isothermal process, we know that P by rho is equal to constant. So by substituting this, we will get a Bernoulli's equation like this, that P1 by rho 1 G log P1 plus V1 square by 2G plus Z1 is equal to P2 by rho G log P2 plus V2 square by 2G plus Z2. Similarly, for adiabatic process, P by rho to the power K is constant. So we will get another Bernoulli's theorem, Bernoulli's equation for compressible flow. So Bernoulli's equation for compressible flow depends upon the type of process. If we will get numerical, it will be mentioned that either the process will be isothermal or the process will be adiabatic, and we have to apply the formula accordingly. Okay. So now this is the two different types of Bernoulli's theorem we get for compressible flow, and we have to remember this. Okay. Now third one is momentum equation. What is momentum? Mass into velocity. We have seen that in compressible flow. Now we have to modify that for compressible flow. So momentum per second of a flowing fluid is equal to the product of mass per second multiplied by the velocity of the flow. Okay. So mathematically, if we want to write, we have to write rho into A into V, that is mass per second multiplied by V. Now this rho into A into V is constant as per compressible continuity equation. We have seen in this. This means that the momentum per second at any section is equal to the product of constant quantity and the velocity, because rho into A into V is the constant. So rho into A into V multiplied by V, what we are doing actually, we are multiplying one constant term with velocity. Okay. So this implies that momentum per second is independent of compressible effect, because both are means it is dependent on the velocity only, because one constant quantity is multiplied by velocity. So momentum equation is independent of the density of the fluid. Hence momentum equation for incompressible and compressible flow is same. Okay. Now the momentum equation for compressible flow for any direction can be expressed as net force in the direction will be equal to the rate of change of momentum as per Newton's second law of motion. So rate of change of momentum is equal to mass per second into change in velocity. Mass per second, mass flow per second is rho into A into V, we have seen, and change in velocity is final velocity minus initial velocity, that is V2 minus V1. Okay, so this is our momentum equation for compressible flow, and which is independent on the density variation in the density, because rho when combined with area into velocity give a constant quantity. So it will be like that one. So this is all about introduction part of compressible flow. In next class, we will see some more things related to that. Thank you.